Now in this lecture we will discuss left coset, right coset and Lagrange's theorem. So let me define first left coset. So let H be a subgroup of a group G. Take an element A in G. So A is any element in the group G. Define a subset which we will denote it as AH. It is defined as the set of elements of the form AH such that H is in H. This subset is called, left coset of H in G determined by A. So when we will change A, the coset may change. Similarly, we can define right coset. So again, let H be a subgroup of a group G. Take an element A in G. Define a subset HA to be equal to HA such that H is in H. So what we are doing is that we are just multiplying A on each element of H from the left, then it is a left coset, and here we are multiplying A from right to each element of capital H, so we will call it right coset. So this is right coset of H in G determined by A. So we will see that when we will change A, this subset may change, and sometimes for different A's this subset may be same. So one thing we can do, we can collect all such type of subsets, and because it is left, so I am writing here L, and this is called the set of all left cosets, means we have collected all left cosets such that A is in G. So A is variable, A is varying, and we have collected all the subsets of the form AH, that is the set of all left cosets. And similarly, we can define the set of all right coset HA such that A is in G. So this is the set of all right cosets of H in G, So this is the set of all left cosets, and this is the set of all right cosets of H in G. So let us see it by example. We will see that a left coset need not be equal to a right coset. We will also see the set of all left cosets and set of all right cosets may not be equal, and in some cases they are also equal. So we will see it by example. So let us do some example. So take a group. Example 1. Suppose I take a group to be clients 4 group and its elements are E, A, B, C. Let us take one subgroup. So I have a subgroup. Suppose I take E, A as a subgroup. Now take any element in G. So suppose I take an element E in G. So for different element we can form the coset. So we can multiply H by E. So when we will multiply H by E, so we have to multiply E to each of the elements of H. So E into E, you will get E. E into A, you will get A. So you will get the same thing as H. Now let us multiply AH. So A into E, when you will do, you will get A, and A into A is A square, so E. So it is again the same thing. Now take another element B, H. So BH when you will do, so you have to multiply B to each of these elements. So B, E, there is a composition in between, and B, A. So if you have any confusion, you can put composition. There is a composition of the group. And what is this subset? So BE is B and BA is C by the definition. Now I have taken E, A, B, and now let us take C. So C, so COE and COA. So what is this? This is C and COA is B. Oh, so both are same. So what we get is that, so this is the left coset of H determined by E, left coset of H determined by A, left coset of H determined by B, left coset of H determined by C. And what is the set of all left cosets? So let us have the set of all left cosets of H, and so one left coset is EH, which is same as AH. So both are as a subset same. So we need not to write it 2 times. So I will write it only 1 time. So and it is also same as H. So let me write H here. In place of H, if you want, we can write AH, EH, or anything. Now again, if you will see, BH and CH are same. So as a set, either write BH or CH. So this is the set of all left coset. This is same thing as I have told just now. It is same thing as if you write AH, BH. It is also same thing as AH, CH, because as a subset AH, BH and CH are same. So a set of left cosets of H in G, either you denote it like this, this, or this, or you may take HCH, HBH, and so on. Now let us also determine the right cosets. So what are the right cosets? In this example, so I first take the element E. So HE, as it is clear from the definition, you will multiply E on this set, then it is EA, which is same thing as H. HA, you will multiply A on both the elements, so EA, EOA, and AOA. So it is AE, which is again the same thing. Now HB, so you will multiply B. So EOB, AOB, so this is B, AOBC, and when you will take HC, then it is EOC and AOC, so it is CB, so both are same thing. So if you will take the set of all right cosets of H and G, then it is again H. It both are same, so you may take HB. Now here one thing you can further see that BH, that is BC, and HB is also BC. So as I said, in place of BH you can also write HB. So HBH. So it is same as the set of all left cosets of H. So it may happen that for some groups they are equal. Now I am going to give you an example where they are not equal. In fact, this group is abelian. So because it is abelian, so either you multiply from left side or right side, it will give you same thing. That's why it is equal. Now come to another example. Now example number 2. Example number 2. So let me take G to be S3. So S3 have 6 elements, identity 1 2, 1 3, 1 4, 2 3, 1 2 3 and 1 3 2. These are the 6 elements of S3. So let me take a subgroup of S3, H to be equal to identity 1 2 3 and 1 3 2. So I take a subgroup like this. So it is not hard to see, identity into H you will multiply, you will get H. 1 2 3 into H, if you will multiply, then you will multiply it by 1 2 3. 1 2 3 into 1 2 3 is 1 3 2. And 1 2 3 into 1 3 2 is 1 2 3. So you can calculate it. And when you will do 1 3 2 into H, you will again get 1 3 2. 1 3 2 into 1 2 3 is identity. So I have done mistake. 1 2 3 into 1 3 2 is identity. So this is identity. And 1 3 2 into 1 3 2 is 1 2 3. So in fact these three things are same. So H is equal to identity into H is equal to 1 2 3 into H is equal to 1 3 2 into H. So we get the same thing. Now 3 element we have used from the group. Let us calculate for the remaining 3 elements. Okay. So 1 2 H. So let us multiply this by 1 2. So identity into 1 2 is 1 2. Second element is 1 2 into 1 2 3. And the third element is 1 2 into 1 3 2. So let us solve it. What will we get? 1 2. 1 is going to 2, 2 is going to 1. So 1 is fixed. And 2 is going to 3. So it is 2 3. Now 1 is going to 3. 3 is going to 3. So this is 1 3. And 2 is going to 1. 1 is going to 2. So 2 is fixed. So this is this thing. And now let us calculate 1 3 H. And 2 3 H. So it is not hard to see, or I am leaving it as exercise, that these 3 are equal. These 3 are same thing. So it means when we will determine the set of left cosets of H in G, then we have only 2 distinct left coset. One is either use one of them or use one of them. So there is only 2 left coset. So let us write it. So G H left cosets. So one left coset is H and another left coset is 1 2 H. There is only 2 left cosets. Or you can use in place of 1 2 H, 1 3 H, 2 3 H, or in place of H you can write identity into H, or 1 2 3 into H, or 1 3 2 into H. Now let us come to the right coset. So let us determine right coset, and on the same way, if you will calculate, this will turns out to be H, and it is not hard to see that this is same thing as 1 2 3, and this is same thing as this. So all the three will be equal. Now let us calculate H 1 2. So this is identity into 1 2, so you will get 1 2 as a first element. Now 1 2 3 into 1 2 and 1 3 2 into 1 2. Now let us calculate 1 2, 1 3 2. 1 2 3 into 1 2, so 1 is going to 2, 2 is going to 3, so 1 is going to 3, 3 is going to 1, and 2 is going to 1, 1 is going to 2, so 2 is going to 2, so this is 1 3. And now let us see this, 1 is going to 2, 2 is going to 1, so 1 is fixed, and 2 is going to 3, and 3 is going to 2, so this is same thing. And again it is not hard to see that this will turns out to be 1 3 and H of 1 2 3, H of 2 3. So again if you will write the set of all right cosets of H in G, then it is H, and you may take any one of these, so let me write H 1 2. Also H 1 2 as a set and 1 2 H as a set, both are also equal. So it means the left cosets and right cosets are equal. When for a subgroup left coset and right cosets are equal, then that subgroup is called normal subgroup. Once again, once for a subgroup each left coset determined by an element A and the right coset determined by that elements are same, then that subgroup is called normal subgroup. We will discuss this in detail in the next lecture. But it is not always true that the set of all left coset and right cosets are equal. When the set of left coset and right cosets are equal, when this is same thing as this, then we simply write it as G by H, that is the set of all cosets of H in G, set of all, because left coset and right cosets are same thing, set of all cosets of H in G. But this is conditional. If these two are equal, then it is denoted as GH and it is called the set of all cosets of H in G. And this happens in the case of normal subgroup. So when the subgroup is normal. So we will discuss normal subgroup later on. Now let me give one more example where they are not equal. So I have given you two examples, one for abelian group, one for non-abelian group, and in both the groups these things are equal. So let me come to another example where these two things are not equal. So of course in abelian group always they are equal. So we have to take non-abelian group, and S3 is the first non-abelian group. So let us have an example over S3. So take another subgroup of S3. Identity 2 3. So I take this subgroup. So this is a subgroup of order 2. So again it is not hard to see that this is equal and this is equal to H. Now take another element of G. So I have taken two elements, identity and 2 3. Now take 1 2. So 1 2 H. So we will multiply 1 2 to each of the elements of this. So this will give you first element as 1 2, and this is 1 2 2 3. So what is this? 1 2. 1 is going to 2, 2 is going to 3, and 3 is going to 1. So this is 1 2 3. Now come to 1 3 H, 1 3 into identity is 1 3, and then 1 3 into 2 3. So this is 1 3, 1 is going to 3, 3 is going to 2, and 2 is going to 1 again. So this is 1 3 2. So we have taken all the 2. Now come to another element, 1 2 3 into H. So 1 2 3 into identity is 1 2 3, and 1 2 3 into 2 3. So what will you get? 1 2 3 into 1 2. 3 is fixed here. 3 is going to 2 and 2 is going to 3. So 3 is fixed. So 1 is going to 2 and 2 is going to 1. And one more element, 1 2 3, and now 1 3 2. Let us see what will happen with 1 3 2. So 1 3 2 H. So 1 3 2 into identity, that is 1 3 2, and 1 3 2 into 1 3 2 into 2 3 2 3. So what is this? 1 3 2. 1 is going to 3, 3 is going to 2, and 2 is going to 1. So 3 is going to 1, and 2 is going to 3, and 3 is going to 2. So 2 is fixed. So this is the element. So if I write all the left cosets of H in G, so these elements are H itself. Again, these two are same. These three are same, so we can write H for it. Now 1 2 H, one 3 H and 1 2 H are different, so let me write 1 3 H. And what about these two? These two are same, so this is same as 1 2 3 H, so we will not write it. And now 1 3 H and 1 3 2 H are same, so these two are same, so we will not write it. So this is the set of all left cosets of H in G. Now on the same way we can determine the set of all right cosets of H in G. So let us do that work also. So H into identity, as you can see, it will be H, and H into 2 3, if you will determine, it will be same. Now let us do for 1 2. So H 1 2. So H 1 2 is 1 2, and 2 3 1 2, 2 3 1 2. So 1 is going to 2 and 2 is going to 3. So this is 1 2. 1 is going to 2, 2 is going to 3, so 1 is going to 3, 3 is going to 2, so this is 1 3 2, and 2 is going to 1. So this is this thing. So you can see that 1 2 H is 1 2 1 2 3, and H 1 2 is 1 2 1 3 2. Now come to another element, H 1 2 2 3 1 3. So let us take 1 3. So H 1 3. So this is again 1 3, and we will take, when you will multiply 1 3 and 2 3, you will get 1 2 3. So check it, not hard to check. Now what about h? So 1 2 2 3 1 2 3. So let us take 1 2 3. So when you will multiply, you will get 1 2 3 first, and then 1 2 3 into h is 2 3. So 2 3 into 1 2 3. So what will you get? It is right. So calculate it, and h 1 3 2, the last coset. So 1 3 2 you will get, and then the next element is 1 3 2 2 3 into 1 3 2. So this is 1 2. So we can write the set of all right cosets of h in G. So set of all right cosets of h in G, and what are these cosets? So one is h12, h13, both are different. Yes, h13 and h123, but 1 2 3 and these two are same thing, and similarly these two are same thing. So no need to write any another element, these are same. But as you can see that the set of all right cosets of h are not equal to the set of all left cosets of h. Why is it happening? Because h12 is not equal to 12h and h13 is not equal to 13h. So it may happen that the left coset for a particular element is not equal to the right coset of a particular element. So once again, why is it happening? Because h12 is not equal to 12h, and similarly h13 is not equal to 13h. So left cosets and right cosets are not equal. So there are subgroups for which left coset and right cosets are not equal, and there are subgroups for which left cosets and right cosets are equal.